In this video series, we shall talk about the foundational law of electricity and magnetism, the Coulomb's law. Most of us by now are familiar with what electric charges are. We know that there are two types of charges in nature, a positive charge and a negative charge. Two like charges always repel each other, which means positive charges repel each other and negative charges also repel each other. Whereas two opposite charges always attract each other, which means a positive and a negative charge attract each other. Now the important question is, what is the magnitude of force with which these charges attract or repel each other? And how does that force vary with charge magnitude and distance between them? Well, for this we have an important mathematical tool known as Coulomb's law. Coulomb's law gives us magnitude of force between two stationary point charges. It was first published by a famous 18th century physicist, Charles Augustin de Coulomb. Coulomb published this law after he conducted several experiments measuring electric forces between two charged objects. According to Coulomb's law, the electrostatic force of attraction or repulsion between two point charges is directly proportional to the product of charge magnitudes and inversely proportional to the square of distance between them. So I repeat, the electrostatic force of attraction or repulsion between two point charges is directly proportional to the product of charge magnitudes and inversely proportional to the square of distance between them. So mathematically, Coulomb's law is simply F is equal to K Q1 Q2 by R square. So let me explain this law in bit by bit detail. If you take two point charges, say Q1 and Q2, and separate them by a distance R, the electrostatic force Fe between the two charges, which can be either attractive or repulsive, is proportional to the individual point charges. Means Fe is proportional to Q1 and Fe is proportional to Q2. It is proportional to both. That means Fe is proportional to Q1 into Q2. And it's inversely proportional to the square of distance between them. That means Fe is proportional to 1 by R square. If you combine all the proportionalities, we get electrostatic force between two point charges Fe is proportional to Q1 Q2 by R square. This proportionality can be eliminated by adding a constant K, finally giving us the Coulomb's law as Fe is equal to K Q1 Q2 by R square. This constant is known as Coulomb's constant or electrostatic force constant, and it has a unit of Newton meter square per Coulomb square. The electrostatic force between charged objects also depends on the medium in which the charges are placed. In case of free space or air, the value of Coulomb's constant K is found to be 8.987 into 10 to the power of 9 Newton meter square per Coulomb square. It can be approximated as K is equal to 9 into 10 power 9 Newton meter square per Coulomb square. In general, when the charges are placed in a medium other than vacuum, Coulomb's constant K as well as the electrostatic force reduces. This is because every medium offers certain amount of resistance to the electric lines of force. Although this force equation Fe is equal to K Q1 Q2 by R square is in its final form, physicists sometimes have a habit of writing the constant K in terms of another constant called epsilon. which makes the Coulomb's force equation as Fe is equal to 1 by 4 pi epsilon q1 q2 by r square, where epsilon is the electric permittivity of medium in which the charges are placed. It is also known as absolute permittivity of the medium. In case of vacuum or air, epsilon is denoted by epsilon naught. We shall learn more about this concept of electric permittivity as we advance further into electromagnetism. As of now, we need to just know that it's a parameter that measures the resistance of a medium to an electric field. A medium in general responds to an electric field by getting polarized, especially if it's a dielectric. That means it forms a collection of dipoles. These dipoles align in such a way that they try to neutralize the effect of the electric field coming from the charges placed in it. Therefore, the electric force between the charges gets weakened by a certain factor. For a specific medium, we can write epsilon of that medium as epsilon naught, which is for the vacuum, into epsilon r, which is the relative permittivity. That means if a pair of charges are transferred from vacuum to a medium, the electrostatic force between them drops by epsilon r times. However, for all practical purposes, F is equal to k q1 q2 by r square. So as mentioned till now, Coulomb's law is an inverse square law, which means if the separation between the charges increases by n times, the force between them drops by n square times. So if the distance between the charges double, the force is reduced to 1/4 of its original value, and if the distance is tripled, it becomes 1/9 of its original value. Likewise, if the separation becomes half, then the force becomes 4 times its original value. In this context, we can observe an analogy with gravitational force, which is also an inverse square law and has the same structure similar to that of Coulomb's law. Because gravitational force between 2 point masses is F is equal to g m1 m2 by r square, as the electrostatic force and the gravitational force are analogous. However, gravity is far weak compared to electrostatic force, more than billion times weaker than electrostatic force. It's evident in our day-to-day observation. Just a small imbalance of charge between two tiny objects such as bits of paper and a Coulomb can cause the bits of paper to fly towards the tiny Coulomb, overcoming the downward pull of Earth's entire gravity coming from a huge ball of 10 to the power 24 kg. Also, gravitational force is always attractive in nature, whereas electrostatic force is both attractive and repulsive. So with this, we'll continue more about Coulomb's law in the next video. Thank you.